Okay, hi everybody. This is the Math 31 applications review. This is question 12. A conical reservoir is 50 meters deep and 200 meters across the top. Okay, so let's just take a quick glance at kind of what that means. So it's 50 meters deep, okay, 200 meters across the top. Okay, so in this case here, the diameter is 200, the depth here is 50. Now, the water is going to sit somewhere over here, but the point is the relationship between the length across the top and the depth of the water is going to be proportional to those dimensions on the overall tank, just because of similar triangles here. Water is being pumped in at a rate of 7,000 meters per minute and drained out at a rate of 9,000 meters per minute. Okay, so what you're being told, and not very directly, but you're being told nonetheless, is that the overall change in volume here is negative 2,000 meters cubed per minute. We are losing water faster than we're gaining it, so we're losing on average 2,000 meters cubed per minute. Okay. The question is, what is the change in diameter? So we're asking for d with respect to t when the height of the water in the tank when h is equal to 20 meters. Okay, well, what we got to do here is figure out some sort of relationship between volume, height, time, and the whole bit here. And the answer to that is the volume of a cone, okay, is 1/3 pi r squared times the height. Okay, now notice that this is in terms of radius. Let's just talk about this for a second, just kind of off to the side here. Notice that 2 times the radius is equal to the diameter. Okay, now if you take the derivative of this thing right here with respect to time, I'm going to get 2 dr by dt is equal to dd by dt. Okay, now that's a relationship between the rate of change of the radius and the rate of change of the diameter that I'm going to come back to in a little bit. Because this question is ultimately asking for the rate of change of the diameter, but my expression here is in terms of the radius. Now, because it's in terms of the radius, and because that's what I'm looking for, I really do want to get rid of the height variable here. I know, okay, that a proportion exists here. I know that the diameter of the cone, which will be 200, compared to its height, 50, will equal twice the radius of the cone compared to its height. Okay? Now, again, this is because this is diameter over height here. Now, 200 divided by 50 is going to be 4. Divided by that 2 is going to be 2, is equal to r over h, which means h is equal to r over 2. So this relationship right here is going to feed back into this equation. And so I'm going to get volume is equal to 1/3 pi r squared r over 2 to get 1/6 pi r cubed. That's now the relationship between the volume of the water in the tank, okay, and the radius of the tank. These are both functions with respect to time. So I'm going to take the derivative. Now, notice that at this point here, it does say when the reservoir is 20 meters deep, but I'm not going to plug that in for height. Okay, I will deal with that in a little bit here. If I plug that in too soon, I'm going to create constants in here that will become 0 when I take the derivative. Height is something that changes with respect to time. This is a specific value that I will plug in later. So I take the derivative right now. dv by dt is going to equal, bring down the 3, and that's going to be 1/2 pi r squared dr by dt. Okay, remember, I am looking for dr by dt. I know that dv by dt is negative 2,000. Okay, I'm going to multiply, well, I'm going to divide here, I should say, by 1/2 pi, and what the heck, I got to divide by r squared. Well, I don't know what the specific radius is. Oh, yes, I do. Because I'm looking for where this occurs at the specific instant that height is 20. if the height is 20, just watch this, the radius will be 40. So this will be over 40 squared. Which means, okay, I'm gonna, let me just think here if I can do this really quickly in my head here. That's going to become 4,000 over 40 squared. I just don't want to screw this up. Whoops. And see, I did it on the calculator over here, so you can't see it, but I screwed it up over here. Oh, and this ends up being, when you simplify that, negative 5 over 2 pi. Okay? Now, if I want to get the rate at which the diameter is changing with respect to time, I simply have to recall that that is equal to twice the rate at which the radius changes. So if I just multiply this by 2, I will get negative 5 pi meters per minute. So I hope that made sense here. Let's just walk through this one real quickly again. So I'm given the dimensions here. Okay, the dimensions allow me to make a connection between the radius and the height because of similar triangles here. The proportion diameter to height allows me to make that substitution, which I can substitute into this expression for volume. I do that to simplify it. I do not plug in, though, the specific value for height until after the derivative because height changes with respect to time. I want to take the derivative first to see how it changes in time. Then I plug in the specific value. And I plugged in the 20 into this, got that r was equal to 40, and then I simplified for my dr by dt and then converted that to dd by dt.